Happy morning, dear friends. Here's yours, Dr. Ajanta. Welcome to Demystify with Ajay. Dear friends, today we are in very much important topic. It is all about future engineering. Building machine learning system and pipelines takes significant efforts. So, which is evident from the knowledge you gained in these previous sessions. So actually the path from data to insights and informations, not an easy and direct one. So it is tough and also iterative in nature, involving data scientists and analysts or machine learning scientists to reiterate through several steps multiple times to get to the perfect model and derive correct insights. So the limitation of machine learning algorithm is the fact that they can only understand numerical values and inputs. So this is because at the heart of any algorithm, we usually have multiple mathematical equations, constraints, optimization, and computation. So hence it is also very much important thing, and I just want to specify one thing. See, actually it is almost impossible for us to feed raw data into any algorithm and expect result. This is where features and attributes are extremely helpful in building models and mainly on top of our data. So building machine intelligence is a multi-layered process having multiple facts. Understanding your data involves understanding the complete scope encompassing your data, including the domain, constraints, qualities, and availability of main attributes. So you might remember that the data is comprised of multiple fields, attributes, variables, whatever you can just specify. So each attribute by itself is the inherent feature of the data. So you can then derive further features from these inherent features, and this itself forms a major part of future engineering. Of course, we are talking here about future engineering. But the main important thing is all about this future. Raw data is hardly used to build a machine learning model, mostly because algorithm can't work with data which is not properly processed and wrangled in a desired format. So features are attributes or properties obtained from raw data. Each feature is a specific representation on top of the raw data. So features can be of mainly two major types based on the data set, that is inherent raw features, so which we just say inherent raw features are combined directly from the data set with no extra data manipulations or engineering. And when derived features are usually what we obtain from the future engineering, where we extract features from existing data attributes. And of course, dear friends, see, actually machine learning, we have already discussed about the pipeline. So machine learning pipeline with the major components identified with various building blocks, it is already there. And of course, I just want to specify one thing, kindly just observe here, dear friends. So when on taking towards the futures, okay, so here our main important thing, it is all about data. Okay, what you're just going to do with the data? Of course, first of all, we have to retrieve the exact correct data or the appropriate required data. Okay, once on required data is retrieved, what you're going to do? Of course, we are going to do an important functionality. Yes, of course, we want to pre-process it, and once done, of course, we have to do about this future engineering or extraction, then towards the future selection or scaling. Okay, done. Once after this doing, what we are going to do? Yes, of course, dear friends, with this, we have to apply our model. apply our model, yeah, this would be our machine learning model. And once with this machine learning model onto this well processed and with applied future engineering with the selected appropriate futures, we apply to the model and which we just obtain it. Yeah, we are just going to evaluate this by using suitable metrics, and we just have the exact resultant of the model. Yes. Once after this, yeah, we are just going to make it towards the one which we are making use in deployment, or yeah, maybe using in monitoring or making some automation. Yeah, this is goes further beyond. If the exact performance, if the performance which you obtained from this model, yeah, is it not satisfied, of course you have to reiterate this. Okay, you have to reiterate this till the satisfactory model performance is obtained. Once if it is not obtained, yeah, you can just change, do some another pre-processing, or you can just go with some other methodology on future engineering or extraction, or some future selection. You can just change or tune up it, and once done, yeah, you can just change the model which you have just previously applied, and then make the again evaluation metrics to check for the performance. So this is what the exact thing going on round and round. So this is one among the main which we just say standard machine learning pipeline. Yes, dear friends, of course we have already done and discussed a lot related towards this data preparation, that is the pre-processing functionalities, and yeah, here we are going to focus on towards this future engineering, and then we are going to travel towards this future selections and scaling. Okay, and here, dear friends, yes, of course, when coming towards this extraction and engineering, yeah, exactly, this is the essential towards the process of transforming processed data into the futures. But processed, that is, we mean the raw data after going through necessary pre-processing and wrangling operations, the exact sequence, how it would be, yes, of course, yeah, you are just going to have the pre-processing, and then you just go with this future extraction and all the things, and third one, you just obtain the future scaling and towards the selection, and then comes the absorbed, that is the exact functionalities of data towards the future. This is how a processed data converting towards the future. So this is very much important, and it is quite evident that based on the sequence of this steps which I have just specified here, yeah, future or first crafted and engineering, so necessary normalization and scaling is performed, and finally the most relevant futures are selected to give us the final set of futures. So yeah, of course, we will cover everything in coming sessions one by one, and now we are just going towards this future extraction and engineering. Dear friends, the process of future extraction and engineering is perhaps the most important one in the entire machine learning pipeline. Good futures depicting the most suitable representation of data that help in building effective machine learning model. In fact, more than often, it's not the algorithm but the futures that determine the effectiveness of the model. In simple words, good futures give good model. A data scientist approximately spends around 70 to 80% of their time in data processing, wrangling, and future engineering for building a machine learning model. So hence, it's paramount important to understand all the aspects pertain to future engineering if you want to perform a proficient machine learning engineering. So here, machine learning engineering is indeed both an art and a science to transform data, as I have already specified, data into a future. So feeding into models. So sometimes you need a combination of domain knowledge, experience, intuition, and mathematical transformation to give you the future you need. By solving more problems over time, you will gain the experience you need to know what futures might be suitable for a problem. So why we are in need of this future engineering? Each and every time I'm just specifying this is what the very important, all the things. Yes, exactly, dear friends. This future engineering, yes. We have already defined, I have just specified that as future engineering is the most thing, and it is the basic pertaining to the importance of future engineering. So I just want to specify some simple important points. So when you just choose this future engineering, yes, it just gives you the better representation of data. What is that better representation of data? Dear friends, actually futures are basically various representation of underlying raw data. So these representation can be better understood by machine learning algorithm. Besides this, we can also often easily visualize this representation. And secondly, yes, better performing. Okay, so better performing model. So the right futures tend to give models that outperformance other models no matter how complex the algorithm is. In general, if you have the right future set, yeah, even a simple model will perform well and give desired results. So in short, better futures make better model. Okay, and yes, next it is essential for model building. Essential for model building and evaluation. Dear friends, we have mentioned this numerous times of now. That is, raw data cannot be used to build machine learning models. So get your data, extract futures, and start building models. Also, on evaluating model performance and tuning the model, you can reiterate over your futures, set to choose the right set of futures, and get a best model. And of course, yes, this when on just choosing a good future engineering, yeah, it is more flexibility on data types. See, while it is definitely easier to use numerical data types directly with machine learning algorithm with little or no data transformations also. See, the real challenge is to build models on more complex data like text, like images, you can just, or videos. So future engineering helps us build models on diverse data types by applying the necessary transformation and enables us to work even on complex unstructured data. And last but not least, yes, this emphasis on business domain. Data scientists or analysts or machine learning scientists are usually busy in processing, cleaning the data and building models as a part of their day-to-day task. This often creates a gap between the business stakeholders and a technical or analytical team. So future engineering involves and enables data scientists to take a step back and try to understand the domain and business better. So by taking valuable inputs from the business and subject matters experts. So this is necessary to create and select futures that might be useful for building the right model to solve the problem. As I have already specified, yeah, dear friends, there are no fixed rules for future engineering. That is engineering making towards the different types of data. So here, what we are just going to do, of course, there are you can have a combination of domain knowledge, Bristol's constraints, handcrafted transformation, mathematical transformation to transfers the data to future. And different data types have different techniques for future extraction. Okay, what are all the data types? Yeah, there is a text, there is an image. Of course, you can just go for numerical data. You can just go for categorical data, temporal data. Okay, so yes, in this session, yes, let me just go towards the futures on categorical data. Okay, so today we are just going to discuss about the categorical data. So let me just have with a session on example with the coding. And yes, dear friends, any attribute or feature that is categorical in nature represents discrete values that belong to the specific, how come we can just say specific types, that is nominal or ordinal. Okay, so yes, I also have to specify that. Yes, let I just give you. Yes, today we are going to discuss on categorical domain. Okay, so categorical data, and here it just has two different things. One is nominal and next one it is ordinal. Of course, we have already discussed in mathematical intuition in statistical part of sessions. And yes, dear friends, this nominal categorical features are such that there is no concept of ordering among the values. That is, it does not make any sense to sort or ordering them. So movies or video games, genre or weather seasons, country names, or some examples of those nominal attributes. When coming towards this ordinal, yes, ordinal categorical variables can be ordered and sorted on a basis their values. Okay, and hence these values have specific significance, such as their order makes sense. For an example, if you just specify something, clothing size or educational levels and so on, so many things are there. Yes, let me just look on to various strategies and techniques for transforming and encoding this categorical features and attributes. Okay, yes, dear friends. So here we are just going to have this particular categorical. So kindly just observe. So yes, as necessary, let me just have use of those inputs. Of course, usually we need to have the basic libraries, import pandas as PDs and import numpy for MP. So this one, yes, including these two, let me just go on to the main thing, transforming a nominal future. Okay, so transforming nominal features, dear friends, as I have already specified, nominal features or attributes or categorical variables that usually have finite set of distinct discrete values. Often these values are string or text. Okay, so text format, and machine learning algorithm cannot understand them directly. Okay, so hence usually you might need to transform these features into more representative numeric format. Okay, so let me just have data. Actually, this exact new data set, it is pertaining to video game sales. Okay, so actually this exact data set is available in Kaggle also, and I also include this in this GitHub, and I just provide you the GitHub link in description or the first command. Okay, okay. Now, dear friends, what this exact data set has. Okay, so kindly just have a note. Let me load it. So here we have our data set. Okay, dear friends, actually the data set depicted in this data frame just shows us various attribute pertaining to video games and features like this platform, genre, publisher or nominal categorical variable. Now let's transform the video game genre features into numeric representation. Do not hear that this doesn't indicate that the transformed futures will be numeric futures. It will still be discrete valued categorical futures with numbers instead of text for each genre. It is going to be a numbers. Okay, so let me just have a one by one. Okay, and I just include this. Okay, so here yes, let me have what are all the genre it has. And yes, dear friends, that output just tells us we have 12 distinct video game genre in our data set. And let's transform these futures now using a mapping scheme. Okay, and by using this code. Okay, and kindly just observed we have used the sklearn pre-processing, and here we are just going to have our genre column. We want to transform it, and with this transformation we are going to make this 12 data and into a numeric representation. So kindly just observe. Okay, what you have happened now. So, sorry, what you are able to see here is, so kindly just see here, dear friends. So from the output, we can just see that the mapping scheme have been generated, which yes, each genre value is mapped to a number with the help of a label encoder. Okay, so that label encoder, here we have, one second, I just show you. Yes, this label encoder, this is the exact object, and with this object only we have just transformed it in a numeric form. Okay, and yeah, dear friends, this exact the genre label field depicts the mapped numerical label for each genre labels. Okay, and yes, let me just have it by executing this. So here we have this genre label, and now kindly just view. So here we go. So see here, this is what the genre label. So platform, it is 4, raising it is 6, and kindly just have see. So the raising it is in 6. Okay, and towards the sports it is labeled as 10. Yeah, that is what here. So you are able to see here. So yes, the genre label field depicts the mapped numerical field or numerical label for each of the genre label, and we can just clearly able to see. Okay, clearly able to see that this is adherence to the mapping that we generated earlier. Okay, now next let me just move on to a simple thing, the same with an ordinal futures. Of course, dear friends, as we already seen, that is future, that is categorical. It has a nominal and an ordinal. So previously we just seen how to handle the nominal. Now let me just have an ordinal value. So ordinal futures are similar to nominal futures, except that order matters and is an inherent property with which we can interpret the values of these futures. So like nominal futures, even ordinal futures might be present in text form, and you need to map and transform them into their numeric representation. So let now load our new data set. Actually it is on Pokemi data set that we used earlier. Okay, and yeah, look at various values which we are just going to have it in this column of future generation. Okay, so this is what the attribute. So kindly just see here, we have attribute as like this generation has the value as like Gen 1, Gen 2, Gen 3, Gen 4, Gen 5 and Gen 6. Okay, and now let me just resample the data set by using this exact code. We are just going to see it. Kindly just see here. We want to see, we can just get a good slice of data later on that represents all the distinct values, okay, so which we are looking for. So from this output we can just see that there are a lot of generations. Mainly here we have total number of 6 generations in this Pokemon database, that is belonging to generations 1 to generation 6. And yes, this generation 1 is were introduced earlier in the video games and the televisions, that in generation 2 and so on. So many things are there. Nothing much more in diving it into the data and towards generation. Okay, so hence they have a sense of order among them. So unfortunately, since there is a specific logic or set of rules involving in case of each ordinal variable, so there is no generic module or functions to map and transform these specific future into numeric representations. So hence we need to do a handcraft using our own logic, or which is depicted into a functionality. So here I have just done with a dictionary. Okay, so by using this exact dictionary, we can able to make that label functionality. Kindly just observe, we are just going to have it into our ordered map, and kindly observe, dear friend. So here we just go. So Gen 2 it is labeled as to 2, Gen 6 it is labeled as a 6, and 4, 3, 1 and 5 of course. So thus you can see that it is really easy to build our own transformation mapping scheme with the help of this Python dictionary, and you can just use the mapping functionalities also, okay, from the pandas to transform the ordinal futures. And yes, dear friends, we have already mentioned several times in the machine learning algorithm usually work well with numerical values. And of course, you might now be wondering, we already transformed the mapped the categorical variable to numerical representation. So why we need more levels of coding again? See, actually the answer is pretty simple. If we directly feed this transformed numeric representation of categorical features into an algorithm, the model will essentially try to interpret these as raw numeric feature, and hence the notion of magnitude will be wrongly introduced in the system. A simple example, see, actually would be from our previous itself. See, a model fit on generation label. So we would think that value 6 is greater than 5, which is greater than 4, which is greater than, and so on. Okay, so while order in important in the case of this Pokemon generations, there is no notion of magnitude here. So generation 6 is not larger than generation 5. And we should suboptimal the incorrect models. So there are several schemes and strategies where dummy futures are created for each unique value or label. Okay, so out for all the distinct categories in any futures. Okay, in the subsequent thing, we are just going to discuss a scheming including one-hot encoding, dummy encoding, effective encoding, and future hashing. So let me just discuss one by one. So first of all, we are here on one-hot encoding. Dear friends, see, consider we have numeric representation of any categorical feature with some as like M as a label. Okay, so the one-hot encoding scheme that encodes or transform the future into M binary future. So which can only contains the value of 1 or 0. So each observation in the categorical feature is thus converted into the vector of size M with only one of the values as 1, so indicating it as active. And see, let's take our this Pokemon data set and perform some one-hot encoding transformations on its categorical features. Okay, so here when I'm just going towards it, see, kindly just see here our Pokemon data frame has this as like our categorical features, that is the name, generation. Yes, I just show you name, generation, and legendary. Okay, so considering the data frame depicted in the server, we have two categorical features. Okay, this is generation and of course legendary. Okay, so depicting the Pokemon generations and their legendary status, first we need to transform these text label into numerical representation. So for that, let me make use of this. Of course, we have already seen how to make it. So here we are making it with the label encoder on towards generation. The same thing, transforming and mapping of legendary or the status. And let we have the same with this data frame. So now we have two more as gen label and legendary label. So let me just see some few datas. Okay, so here kindly just observe, dear friends, the future as this gen label and this legendary label now depict the numerical representation of our categorical futures. Okay, now let me apply one hot encoding scheme on this future using the code I just show you. Lightly scroll here. So yes, whatever, I'm just going to make it on this generation future, the same things on this legendary. So kindly just observe, dear friends, here we are transforming that label and we are making it with the classes. And this exact data frames we are extracting it with this see, this is a variable. Okay, so this variable which it just makes this transformation of this one hot encoder functionalities, and the same thing it is applied here in this, okay, in this legendary status also. Now you should remember that you can always encode both the futures together using the fit and the transform. So that is what I have used wherever it is needed. So kindly just observe it. And this exact functions by passing in a two-dimensional array of two futures. Okay, so but we are depicting this encoding for each future separately to make things easier to understand. So that is what I have just specified. This is for generation label and here it is for legendary status. Okay, so we can also create separate data frame and label them accordingly. Okay, so for labeling them, let me just make use of this code snippet and kindly just observe. I execute this. Okay, so here we just go with this data. So future set depicting one hot encoding futures of this Pokemon data frame. Okay, the generations and legendary. So kindly just see here, for generation label we have Gen 1, Gen 2, Gen 3, Gen 4, Gen 5, Gen 6. Okay, and towards this legendary we have the legendary label, and this 0 and 1 here it is represented as like legendary false and legendary true. See, from the result of this futures itself that we are clearly see that new one hot encoding future as well as generation label and legendary label, each of these one hot encoding future that is in binary in nature. Okay, so if they contains the value 1, it means future active for corresponding observation. And here when you just go towards this row 6, kindly just see here we are having our Gen 4, that is it is of Gen 4 and where the label it is in 3. So mapping starts from 0, kindly just remember that. So starting from 0, this Gen 4 we are having it as like a 3, and the corresponding one hot encoding future, kindly just observe Gen 4 here we have 1, the value as 1, and remaining one hot encoding futures are zeros, and kindly just observe this. And similarly the legendary status, actually it is true, corresponding to its label it is 1. So and the one hot encoding future that is a legendary true, here we have 1 as and indicating it is active, and towards the false we just hit the 0. So suppose we use this data in training and building a model, but now we have some new Pokemon data for which we need to engineer the same future before we want run it towards our trained model. So we can use the transform, that is fit and transform. So here we are just want to transform the function for our label encoder and one hot encoder objects, so which we have constructed here to engineering the futures from the training data. Okay, so let me just make use of it to have all the columns, and let me just have an use of it. So see here, if I just specify 0 and generation 3 and true, see actually we will follow the same process before, which we just first converting this text category into numeric, and by using our previous label encoder objects, let me just depict it in this functionality. So kindly just see here, this is our new Pokemon data frame. We have a particular name, generation and legendary. Okay, so in such a case, this exact transform would just make the label. Okay, so label encoding, it is applied here. Okay, which we have already done and called here. I just show you 1 second, dear friends. Okay, so see here, this is what. So to make use of this one, so gen LE, that is of generation label encoder, and yes, we are using that, and we are transforming our new Pokemon data. And kindly just observe here towards this data. Let I just execute. So yes, a Pokemon generation label, here we just get it 2, and for the legendary true we just get label as 1. Okay, and yeah, we can also use this particular thing by a label encoder and perform one hot encoding on this new data observation by using this. So one hot encoding, and let me just observe the data. So see here, for this new data we have, so yes, for generation 3 the label is 2, and yes, label is 2, and kindly just see here, generation 3 has the value 1, and to the same true functionality, so the legendary true has the 1 value. Okay, so thus you can see how we used this fit and transform function to engineer futures on our data set, and then we were able to use the encoder object to engineer futures on new data set using this transform. So function this on the data, what is obvious thing. Okay, and yes, specifically the distinct categories and their corresponding labels and one hot encoding. And dear friends, actually you should always follow this workflow in future for any type of future engineering when you deal with training and test data set, when you build models. And dear friends, pandas also provide a wonderful function called dummies. Okay, so called to actually 2 dummies we have, so which helps us easily perform this one hot encoding. And let I just show you by using this panda as get dummies functionality. So see here, if I just specify it with a Pokemon data frame as like a generation, so when on just making this, I want to concatenate that name and generation. Kindly just observe here. So here generation 2, yes, we have this generation 2 as true, and others are all with false functionalities. Okay, so this is how you can just make use of it. Yeah, even you can just make it towards this true and false in int, that is if you just make it as a transform to integer, yeah, you just get it as zeros and ones. So the output depict that one hot encoding scheme for this Pokemon generation values, similar to what we have already depicted in our analysis. Okay, yes, next let me just move on to this dummy coding scheme. So dear friends, this exact dummy coding scheme is similar to that of one hot encoding scheme. So except in the case of dummy coding scheme, we applied on a categorical with M distinct label. So m distinct label, we get m minus 1 binary futures. So thus each value of category variables gets converted into a vector of size of m minus 1. That is what, simple. Okay, so yes, kindly just observe here the same thing what we just done in this previous. So when on just making here, so here kindly observe this gen 2. So the first dropping the first level binary encoded. Okay, so we are making use of drop first. I have just given this true. So sorry, given the true. So in such a case, to drop the first binary encoded future gen 1, and we just got this output. Okay, and if you want, yeah, you can also choose to drop any categories. If you want to drop even the binary encoded level future 6, yeah, you can just use it. So see here, you can just make use of the last one and make it one future. And yeah, you can just drop that last also, or whichever you want. Yes, you can also choose any of your functionalities. Okay, yes, dear friends. So thus from these outputs, you can see that based on an encoded level binary futures which we can drop, and that particularly categorical value is represented by vector or encoded futures. Okay, so here which it all represents here as false, actually it should be in 0. Okay, so yes, for example, in the previous session we have just seen about the future set, and here on towards this Pokemon data frame we have just done it with gen 6 or gen 1, which is represented by all zeros or ones, or here it is as like false and trues or encoded dummy futures. Next, I just want to move on towards effective coding scheme. Dear friends, the effective coding scheme is very similar to the dummy coding scheme in most aspects. However, the encoded futures or future vectors for a categorical value that represent all zeros in the dummy coding scheme, okay, is represented by minus ones in the effective coding scheme. Okay, so let I just give you this. So kindly just observe here. So this is what? So as I have already specified, minus 1. Okay, so this one, see, when on specifying towards this, we can clearly see from that output that which sets to all other thing as like a false. Okay, that is zeros have been replaced by here as minus 1. So when on going towards this gen 6, all the things it just goes towards minus 1, other than the one, this is the zeros, now it is replaced with minus 1 in the case of values, which were previously it would as like a zeros. So as it is in text, yeah, it is in false. And 0 is the exact dummy coding scheme. Okay, yes. Yeah, next we are just going here towards the topic future hasing scheme. Dear friends, the future hasing scheme is another useful future engineering scheme for dealing with large scale categorical futures. See, in the scheme, a hasing function is typically used with a number of encoded futures or preset. Okay, so here as a vector or predefined length. So such that the hashed values of the futures are used as indices in this predefined vector, and values are updated accordingly. So since a hash function maps a large number of values into a small finite set of values, multiple different values might create the same hash, which is termed as collisions. So typically a signed hash function is used so that the sign of value obtained from the hash is used as a sign of value which is stored in the final future. Okay, at the appropriate index. Of course, I have to specify that. So this should ensure lesser collision and lesser accumulations of error due to collision. So hashing scheme works on string numbers and other structures like vectors. Okay, you can also think of a hashed output as a finite set of bins, for an example h bins like that, and such that when hash function is applied on the same values, they get assigned to the same bin out of that h bins based on the hash values, and we can assign the values of h, which becomes the final size of encoded future. So for each category, each okay, so each category of this, we can assign the value of h, which becomes, and we encode use the future hashing. So, for an example, see that even if we have over 1000 distinct categories in a future, we set it h is equal to 10. Why? Yeah, of course, see the output future set will still have only 10 futures as compared to the 1000 futures if we use to one hot encoding scheme. So let I just give you a small thing. See here, we know in this video game data frame. Of course, kindly just let I execute it, and you can also have, yeah, of course, totally 12 genre or that. Okay, so we can clearly see from this output that there are 12 distinct genre, and we used an one hot encoding scheme on genre futures, and we would end up here with 12 binary futures. Instead, we will now use this future hashing scheme by leveraging this Scikit learns. Okay, so let I just use this by using this future hash class. Okay, we use a signed 32-bit. Okay, we use a signed 32-bit version of this functionality. Let I just make use of this hash function. Okay, and yeah, by using this hash function, let me just preset the future with the 6. Of course, we have 12 genre here, but even though, let me just make use of here as a 6, and kindly just observe, yes, just a 6, 0 to 5, it has been done, and each and everything. By using this, yeah, it is clearly seen that from the result future set that the genre categorical future has been encoded using this hashing scheme into 6 future instead of 12. We can also see the rows here. There is a 0 and 5 denote the same genre of this platform and towards the sports. Kindly just observe here. And there's a platform actually which has been rightly encoded into the same futures which we already expected. Excuse me. So yes, dear friends, see as we wrap our session on this future engineering, mainly remember that handling categorical data is crucial to unlocking the full potential of your model. Excuse me. So whether you are transforming nominal futures or dealing with ordinal futures or encoding categorical futures, each steps require careful consideration. So mastering these techniques allows you to turn raw data into a powerful predictors. So setting the stage for a robust and accurate machine learning model. Kindly, dear friends, practice it. You have to practice with so many data set. You have to practice with different types of, as I already specified, as a categorical, with the nominal data, with the ordinal data. Kindly just make use of practicing. Here, let me just end up this session on categorical data, and see you in another session for numerical data. Hope, I think so, this exact video would be useful for you. Kindly just like it, and yeah, for more videos and more information, updated videos on machine learning, kindly just subscribe the channel and share this exact video to whomever it is needed. Okay, happy learning, dear friends. Thank you.